This is a lesson on how to incorporate centripetal acceleration into classical Newtonian force analysis. Just as a reminder about centripetal acceleration arises when something is moving in circular motion. Because the velocity vector is changing, there must be an acceleration. The magnitude of this acceleration is given by this equation, v squared over r. Remember, v is the tangential or linear velocity at a certain point. And because of the relationship v equals omega r, you can see that the angular speed can be related to the centripetal acceleration as well. R is always the distance to the center of the circular motion, the radius of the circular motion. I will also remind you of the four-step force analysis strategy. When you are solving Newton's second law problems, remember to draw your free body diagram. If you miss any forces or if you get extra forces, you're not going to have the right equations. Remember to draw a coordinate system and decompose any forces as needed. And as I'm noting here, when you apply Newton's second law, you write ma on the one side of the equation, wherever that is, and instead of just having just some linear acceleration, we can plug the expression for centripetal acceleration in there. Once you do that, set up, identify your knowns and unknown quantities, and solve, and reflect on your answer, of course, to see if it makes sense. The problem I've chosen for us is a child swinging a yo-yo in a vertical circle. And I'm just going to take a moment to say, sometimes this is misinterpreted like this. This to me is a horizontal circle, as opposed to this being a vertical circle. And if you can imagine swinging a yo-yo in a vertical circle, at the bottom and at the top, you will feel a different tension in the string as you move it in a circle. And you can see that's what the question's asking about. Determine the tension in the string when the yo-yo is at the top of the circle, the bottom of the circle, and moving directly upward. So like at the side of the circle. They give us some information here about the swinging yo-yo. It is at a constant speed, resulting in a period of motion. So we have a period of motion, and I can write that down. We can relate it to omega pretty easy. Remember, omega can be expressed as 2 pi radians, which is 1 revolution, and it takes the period of amount of seconds in order to travel it. So I can write this down, 2 pi radians, half a second, and I will write this as 4 pi radians per second. Wherever I see omega in the equations, I can write that number, and it's a number 4 times pi. The other thing they say in here is the string on the yo-yo is 1 meter, which may look like a length, but we're going to identify that as a radius of motion. If the yo-yo string is a meter, that's the radius of motion. And then also they give us the mass of the yo-yo. It says 85 grams, but I wanted an SI, which is kilograms, so you can do the conversion and get 0.085 kilograms. So all of my knowns are identified over here. If I'm doing Newton's second law, I need to draw a free body diagram, but let me draw a general sketch first of what's going on. We have the top of the motion and the bottom of the motion. We can imagine this moving in a circle with an angular speed omega around and around. And it looks like part C here, when it's moving directly upward, will be on the right side of the circle, so that this yo-yo travels. And all of these velocity vectors are the same length, but they're in different directions. So that's why there's the centripetal acceleration. Here's the center of the circle. I'll just make note of that. Let's set up in a free body diagram. Part A asks for at the top of the circle, so I'll put that at the top of the circle. Let's draw the yo-yo at the top of the circle. At the top of the circle, we're going to notice that the yo-yo has a mass, so therefore it has a weight, so there must be a weight downward. Also at the top of the circle, there's a string pulling it downward, right? If the string wasn't there, the yo-yo would fly off, so that there's also a tension downward at that point. I'm going to write in the acceleration. The acceleration must be towards the center of the circle at that point, so the centripetal acceleration is pointing downward as well. With all that identified, I'm going to assign a coordinate system. And because the acceleration is downward, I'm going to make downward positive. And I'll just call this the y direction. It's a vertical direction. That's perfectly fine. And we can see that this is a 1D problem. 1D Newton's problems are pretty easy to solve. I have the free body diagram, I have everything assigned, and I'm going to set up my equation here. The net force, or the sum of forces, equals ma, and A happens to be centripetal in this situation. Over on this side goes all of the forces on my free body diagram. I'm going to note that I just have two of them, and they're both in the same direction, in the positive direction. So I have T, and I'm going to call this T top, for T for top. And then also the weight is downward, so that's a plus sign, and then that will equal m omega squared r. I'm just plugging in what I know for centripetal acceleration right there. We're asked for t-top, so I'm going to solve it on one side, and then I'm going to have everything else on the other. M omega squared r minus the weight. You may see why I leave this in symbols rather than plugging in numbers. I can get a little bit of simplification going on. Weight is mg, and I can factor an m out. I get omega squared r minus g. Plug numbers in, 0.085. I have omega squared, which is 4 pi squared, times the radius, 1, minus the gravity, which is 9.8. And when you plug this through your calculator, you get 125.89639 newtons. This may seem pretty familiar from what you're already acclimated to with solving Newton's second law problems. The only difference is that the acceleration happens to be centripetal, and you can put in this expression. Otherwise, it's very straightforward to all of the other problems that we've been solving, especially in one dimension. So there's the answer for A. We can look at B. B wants at the bottom. So let's draw a free body diagram of the yo-yo at the bottom. The yo-yo at the bottom still has a weight. There's still a weight on the yo-yo. It still has a mass. This time, the tension will be pulling towards the center, if you can imagine that. The tension pulling upward at the bottom rather than downward. And then also the acceleration needs to go in here. The acceleration will be towards the center of the circle. So in this situation, the centripetal acceleration is upward, as opposed to at the top when it was downward. So when I do a coordinate system for this one, remember I did a coordinate system. When I do a coordinate system for this one, I'm going to choose the direction of positive in the direction of the acceleration. So again, here's plus y. We can put that on here, plus y. And tension will have a positive sign. When I put weight into the equation, I'll note that it has a negative sign. I have to take into account they're pointing in different directions. So when I write out Newton's second law, the net force, the sum of forces, has to equal MAC. It happens to be centripetal. Over on this side goes the forces on my free body diagram. T at the bottom is pointing upward. We'll put B for bottom. And then we have the weight pointing down, and that has to equal m omega squared r. And you might want to take a minute and compare it to, right, when it was at the top as opposed to when it was at the bottom. We got this change in the direction of the weight. Okay. Let's solve for T bottom. T bottom equals m omega squared r plus the weight. And you can probably see where this is going. I'm going to plug in mg here. I can gather m out front and have omega squared r plus g. I can plug in numbers, 0.085 times 4 pi quantity squared. That means the 4 gets squared and the pi gets squared, times 1 plus 9.8. Run this all through your calculator. You get the tension at the bottom is 142.55639 newtons. And when I look at these, remember step 5, let's think about our answer. Does it make sense? Well, I really don't have any way of saying, well, is 125 newtons or 142 newtons, is that a reasonable tension? Seems okay. It's not in the thousands and it's not like decimals, so that makes kind of sense to me. What I will compare is the two values. Which one do I expect to be larger? And when you were thinking about it earlier, when you had the vertical circle, you can imagine it'll be harder. You have to pull up more at the bottom in order to get it to move upward, rather than when it's at the top and it's sort of coasting through the air. And so that you see that the tension at the top is smaller than the tension at the bottom. So you can see this one's bigger and this one's smaller. And so I'm kind of confident that my numbers are turning out okay if you're thinking like on an exam or something like that. Through the magic of video, I have created some space for us to be able to do part C on this problem. And part C asks about when the yo-yo is on the side moving upward. So let's see, at the side, let's draw a free body diagram. If I draw a free body diagram of the yo-yo at the side, I know there's a weight. There's the weight. And I also know that the acceleration, when I look at it, the acceleration is directly inward towards the center of the circle, which would be left, right? A centripetal. And so that's the only acceleration. It's not accelerating in the vertical direction. Remember, it's moving at a constant speed, and therefore it won't be accelerating up or down. It just has to be accelerating inward. And when I think about that, that means that the tension has to be doing something interesting out at the side here. Not only will it cause the centripetal acceleration, but it must counterbalance the weight, or else the yo-yo will slow down. So when I look at the tension at this point in time, it's going to be at an angle relative to straight inward. So here's the angle theta. And it will have a Tx component and it will have a Ty component. I'm making this angle kind of small because it is small. When you calculate it, we'll see how small it is. All right. So when I look at this problem, it's no longer just a one-dimensional problem. Notice I have a Tx and a Ty, so I need to assign a coordinate system that has an x and a y axis. So I'm going to have upward as positive and to the left as positive, and I have to the left positive because that's the direction of the centripetal acceleration. So when I look at this, we're asked to find the tension here. And the tension has two components, y and x. So I'm already thinking ahead a little bit that the tension has to be a hypotenuse. I'll end up using Pythagorean theorem. And I can use the x direction to find Tx, and I can use the y direction to find Ty, and then I can combine those two together. Okay, so that's my general strategy. Let's go ahead and do some Newton's second law stuff. Let's say the sum of forces, I'm still in blue. Do I want to do the x or the y direction first? Doesn't matter. If I do the y direction, it seems like I can get Ty pretty directly. And if I do the x direction, that's not a bad equation either. Let's do the x first. The sum of forces in the x direction has to equal ma in the x direction. And notice in the x direction, the acceleration is the centripetal acceleration. In the x direction, the only force in the x direction is Tx. And I'm going to note that Tx has to be T cosine theta, as I've defined theta in the problem. And I will set that equal to m omega squared r. I don't know theta and I don't know T, which means I have two unknowns, and I'm okay with that because I already have planned to do of force analysis in the y direction, right? The net force in the y direction has to equal ma(y). We're going to note that in the y direction, remember it's not accelerating in the y direction, so this term over here is 0. We're going to see that Ty upward, which is T sine theta, minus the weight downward has to equal 0. These two balance each other out, and I kind of hinted at that earlier. Ty and omega and w are in the same direction. So I get T sine theta equals mg. Okay, so we have two equations, two unknowns. That's good to go. I'm going to call this equation 1 and this equation 2 and use this opportunity to teach you a trick about how to solve when we have an unknown angle and it's buried in a trig function. A nice thing to do in this situation is to remember the property that sine theta over cosine theta is tangent theta. Sine theta over cosine theta is tangent theta. And notice that creates one term for theta rather than having two. And watch what happens when I do this. I'm going to take equation 2 and I'm going to put it over equation 1. So equation 2 is this. I'm just going to write out t sine theta and put mg. And then I'm going to put the second equation on the bottom. All right. The second equation is t cosine theta. Cosine theta. And that has to equal m omega squared r. Now, if you're keeping track of the algebra, a few things cancel. Notice this unknown tension cancels here. We have sine and cosine combining together for what I expected for tangent theta. And also over here we have the mass canceling. We didn't even have to calculate the mass. So we get g over omega squared r, which means I can find that angle. Theta is the inverse tangent of 9.8 over 4 pi quantity squared times 1. When you run that through your calculator, you can get theta pretty easy. Theta happens to be 3.55 degrees. Now that I know theta, I can plug it into one of the other equations. It doesn't matter which one. I plug it into. And so let's see, t equals m, which is 0.085. times g, 9.8, divided by sine of the angle, 3.55118 degrees. When you run this through your calculator, you get 134.4846 newtons. We didn't even have to use Pythagorean theorem for this part. You could have calculated those and then used Pythagorean theorem, but it's just as easier to plug in what we know about theta in there and solve for the tension.